All right, good morning, everyone. My name is Bill Roos. I'm with 3D Vision Technologies out of our Louisville, Kentucky office. Today's webinar in our How to Solve It webinar series is Get Santa's Sleigh Running at Mach 1 in SOLIDWORKS Flow Simulation. So welcome, everyone. And so as you can see from our title of today's webinar, what we want to do is help Santa get around the world in his sleigh. So to get around the world quickly, his sleigh needs to withstand the aerodynamic forces that are applied to it. And today I'm going to show you how we can use SOLIDWORKS Flow Simulation to help ensure that Santa's sleigh is up to the challenge. A couple of notes. By all means, during today's webinar, if you have any questions, please type them into the questions panel. I probably will not answer them during the webinar itself, but I will address any questions at the end. So please do use that if you would like. So today, tools we're going to use is obviously SOLIDWORKS Flow Simulation. And just a couple of things to note here. The CAD model that this webinar is based on is from GrabCAD user Trinity SCSP. And the link to the files you can see there just below the GrabCAD reference. And then also Ryan Field, 3D Vision application engineer, one of my colleagues. He did a webinar just a couple of weeks ago to design that fairing for the front end of Santa's sleigh that you see on the picture of the lower right. So thank you for the CAD models from GrabCAD and also Ryan Field. So today, one of the things that you would want to think about when you're using SOLIDWORKS Flow Simulation is what are we really interested in solving for? For instance, we might be interested in things like drag force or lift force. Maybe we want to calculate the coefficient of drag. Just find out what the overall forces acting on our geometry is based on what happens from the fluids, or maybe even review a shock wave if there is one, from a high-speed sleigh, if you will. So for today's webinar, there's actually 3 different scenarios that I'm going to solve. The first is Santa's sleigh when he's on the ground, and I'll set that up with the sleigh moving at 25 miles per hour. And then what I'll do is clone that particular flow project, and we'll get our sleigh flying at 1,500 feet altitude at a speed of Mach 1. And then once that one is complete, we'll do another one with the sleigh still at 1,500 feet of altitude, also flying at Mach 1. And we're going to add the fairing from Ryan's webinar just a couple of weeks ago to see if it either helps or hinders our aerodynamic performance. So here are the steps that we're going to go through. We'll set up a flow project. We'll add any necessary boundary conditions. We'll set up the goals, in this particular case, the things that we're interested in tracking for our aerodynamic capabilities of Santa's sleigh. We'll create an equation goal for the drag coefficient, and then we'll solve the model. And once all that's complete, we'll start to generate results from our CFD solution. So here's what we're going to do, step-by-step guide. We're basically going to use what's called the wizard in SOLIDWORKS Flow Simulation to get everything set up. So as you can see, these are the things that we're going to need to do just for getting our flow project started. So I'm going to go ahead and switch to SOLIDWORKS and show you how that works. I already have my flow simulation add-in turned on, and this is the CAD configuration that I'm going to work with up front. We have our ground here where my cursor is, and we also have Santa's sleigh sitting on the ground, and then that very pale volume around the sled, that's a mesh control body. We're going to use that for one of the things that we set up inside Flow Simulation. All right, so let's go ahead and get started with our wizard. And we'll call this Santa's Sleigh webinar. And we'll choose a unit system here. I have one that's predefined for what we're going to work on. And we'll set this up as an external analysis. And we're going to add in our fluid. So as you can see, as I'm using this wizard, this is just a step-by-step process for setting up some initial conditions. And make sure we get that going in the right direction. All right, so here, that initial velocity parameter That minus 11.176 meters per second is the fluid moving through what's going to become our computational domain at essentially 25 miles per hour. All right, so that is the initial portion of the setup, and I'll zoom out just a little bit. Now that gray box that you see around the sleigh and the ground, that's what we call our computational domain. So now that you can see what it takes to go through the wizard, we'll take a look at what are the next things that we need to do. Well, we need to add the necessary boundary conditions for the sleigh on the ground. Well, that includes what's called a real wall boundary condition to represent the sleigh ground speed. Then we're going to do a couple of different things like component control. We're going to make that mesh control body transparent to the fluid. We'll add some mesh refinement around Santa's sleigh with that mesh control body. And then we'll add some goals for force and drag and lift for Santa's sleigh. One thing to note is the equation that I'm going to create for the drag coefficient is a highly idealized drag coefficient. In fact, it's really meant for an estimate of drag coefficient around a cylinder in flow. Clearly Santa's sleigh is not a cylinder, but hopefully you get the idea for what we're going to do here. A couple of things to note about the equation. FD, that's our drag force. We'll get that from a goal in SOLIDWORKS Flow Simulation. Rho, that's our fluid density. V, that's the fluid velocity that we're looking at that's going to be hitting the front of Santa's sleigh. A, that is the frontal area of the body that is exposed to the fluid flow. And then ultimately we're calculating CD, that's our drag coefficient. All right, so let's go back here. So we need to make a couple of modifications. The first is I need to modify that computational domain. So we're just taking into account the size of the region around the sleigh. So we'll shrink that down a little bit. And then we'll rotate it around and modify it like so. All right, so now we're just analyzing what happens around the sleigh. Next thing we need to do is use component control, and this is where we're turning off that mesh volume so it's transparent to flow. Our boundary conditions actually were already taken care of when I set up everything for this study. So our initial conditions, 0 degrees C, and there's our fluid velocity. So we don't really have any additional boundary conditions there, but we do have a couple of different goals that we need to put in. So we'll do some surface goals here, and our surface goals, we're going to use the sleigh, and we want to track a couple of different quantities. So we'll come down in our list here, and we're going to track the force in X and force in Y. All right, so for this first one, this is, by the way, the force in X is going to follow our global coordinate system. So I'll call this drag force. And then the force in Y, since that follows our global coordinate system, we'll call this one lift force. All right, now I don't recall the full equation and all the parameters, but I'll give you a rough example of what we would need to do for the equation goal. So here, what we would have to do is we'll start an equation. It's 2 times the drag force, and that is going to be divided by the density of the fluid, which we'll put in a number there. It's not the exact number. The velocity squared, which was 11.176 squared, and then we'll multiply that by the surface area, which was a very small number in meters squared. The other thing I want to do is I'm going to make sure that this is the absolute value, and assuming that I have everything put in correctly, we'll get our equation goal, and that's actually drag coefficient, CD. All right, no issues for misspelling if I did that. And then the last thing that we're going to do, we're going to insert what's called a local mesh control, and we'll do that on that body. And what we'll do is we'll just refine the fluid cells and then the partial cells, which is where the fluid and the structure come together. So those are really the things that we would need to do for setting up the rest of the project. So let's switch back and see if I got ahead of myself. All right, so really the key things that we definitely need to do for checking out the aerodynamics of Santa's sleigh is make sure that we add our force goals and we put in the correct equation for calculating drag. So at this point, what we would do would be solve the flow simulation project. So I'll just cut to the chase here a little bit. I'm not going to solve this live. It takes about 6 or 7 minutes to run this. So what I am going to do is switch to a pre-solved flow project so we can take a look at what happens when Santa's sleigh is running on the ground. All right, so my pre-solved project is this one right here called Santa's Sleigh. And we'll go ahead and load the results in. And a couple of things to note. So some things that you would do when you're working on this, after you create your project, you're going to create a mesh around your components. So here is a cross-section of the mesh. And then one of the things that we really need to do to get a decent result, since we're looking at drag and lift forces, is we need to have enough mesh resolution around our sleigh. And that's where you can see these little cross-sections of the cells for SOLIDWORKS Flow Simulation. I could take a look at the mesh at a number of different locations. For instance, if I get rid of the first one there, we could also take a look at what the mesh looks like around the different regions on the sleigh. So we'll go ahead and clear that out. All right, so let's go to my results view here. And then we'll start to bring in just a little bit of our post-process results for flow simulation. All right, so here we go. The first one, this is a pressure cut plot. And what this shows is the different regions of pressure of the fluid as they hit the front of our sleigh running on the ground at 25 miles per hour. So as I zoom in, you'll see that we have a little bit of a high pressure right at the front of the sleigh, obviously where we've got that nice little scoop there. We have a little bit of recirculation inside the sleigh seat and where Santa keeps all his toys, and then obviously a little bit of vortices and whirls once we get past the sleigh in our fluid. Another thing that you might be interested in would be taking a look at the fluid velocity. So we'll just switch our output there. And here we can see what the velocity of the fluid looks like. So those vortices, you can see where you have the dead space in the fluid as your sleigh is moving along the ground. So we'll go ahead and clear that. And then go back and look at just a couple of other things. So that's really just cut plots. There's a number of other results or post-processing things that we can get from SOLIDWORKS Flow Simulation. For instance, surface plots, that's the picture shown. We could also do flow trajectories, isosurfaces, goal plots, lots of other post-processing information. Let me go ahead and show that surface plot. We'll bring that in so you can see what's happening. We don't want velocity there. We'll switch that to pressure. And we'll go ahead and we'll bring in flow trajectories. All right. And this is really one of the neat things. I really like showing this in flow simulation. So flow trajectory shows us basically where the fluid is entering and then flowing in and around our computational domain. So here I'm taking a look at the flow trajectory of pressure as it's flying into and towards our sleigh or Santa's sleigh. So really cool output that you can get taking a look at basically how that fluid is moving through our computational domain. So cool stuff there. We'll go ahead and stop that and clear that out. And then one of the last things that we would want to do, we would take a look at those goals that we had set up. And the goals are basically how well did Santa's sleigh do for drag force, lift force, and what was our calculated drag coefficient. All right, so that is in our goal plot, and there are the values right there. Okay, so Santa's sleigh running on the ground at 25 miles per hour. We have a drag force of 0.228 newtons, a lift force of 0.23 newtons, and a idealized drag coefficient of 0.747. So that is one of the ways that we could solve what happens with Santa's sleigh when he's maybe getting ready for takeoff or just cruising around with a reindeer pulling his sleigh. So the next thing we're going to take a look at is, well, things that we did. We set up the flow project, we added our boundary conditions, added a number of goals, created our drag coefficient, and then went through the solution and generated a number of results from SOLIDWORKS Flow Simulation. The next thing that we need to do is we're going to clone this original project and modify our boundary conditions to match Santa's sleigh flying through the air at Mach 1. And then we'll go through the steps of solving and generating results from our CFD solution. The general things that we need to do once we have cloned and modified the project is we need to remove the ground from the scenario so that we're flying Santa's sleigh in the air, which means we're going to delete that real wall boundary condition. We're also going to change our ambient pressure and initial velocity to match flying at 1,500 feet. So we'll go ahead and switch back here, get out of our goal plot. And what we're going to do is we're going to clone this particular study. So this is Santa at Mach 1. And we're going to tell Flow Simulation to use the sleigh at Mach 1. All right, so we'll go ahead and let Flow reset our computational domain and our mesh settings. And let's see, we don't need that, so we'll delete that real wall boundary condition. And let's see, I need to hide my mesh control there. We'll go ahead and hide that component there for it. It's a little easier to see. All right, so a couple of things that we need to do. We need to go into our general settings, and we'll change our initial conditions. So at 1,500 feet altitude, the ambient pressure is around 96 kilopascals. And then Mach 1, in this case, we need to change that. Mach 1 is roughly 335 meters per second. So we'll make those modifications to our initial settings. We don't need to change our lift force, our drag force goals, or recalculate our drag coefficient. Just changing those boundary conditions is sufficient. We can zoom out. We have a different computational domain. If we wanted to resize this, we could do that here as well. So from this point, the steps would be the same. I would go into Mesh and then solve this particular project. So what I'm going to do is switch over to my saved version. And what we would take a look at from here, same as before, what are my cut plots? What does the pressure in front of the sleigh look like? What do our velocity cut plots, fluid density, and so forth? What do those all look like when our sleigh is flying through the air at Mach 1? So we'll go ahead and hide this. And just as before, we need to load in our results. And this time around, we'll get into results view here. And we'll go ahead and show that same pressure cut plot. So here what you can see is when we're traveling at Mach 1, we have a very high buildup of pressure at the front end of Santa's sleigh. And then just as before, some recirculation, low pressure not only in the sleigh, but also immediately behind the sleigh. We can also take a look at our velocity plot. And there we can see the relative fluid velocities moving around the sleigh. So a number of different areas where the fluid flow actually goes above Mach 1, which would be somewhere right in here, about the 335 range. So anything that's in this orange to red area is above Mach 1. And the next thing that we would want to do would be review our goal plot for Santa's sleigh here. In this particular case, since we're, well, we have removed the ground, but now that we're flying at a much higher speed, or much higher velocity, we have a higher drag force. Our lift force actually increases, but we also have a very exaggerated idealized drag coefficient. So you can see the values there. And then what I'll do is just switch over for comparison purposes. So our drag force is now 262 newtons, a lift force of 118 newtons, and a drag coefficient of almost 860. So there, we cloned our project, modified our boundary conditions, solved the flow project, and did our post-processing of the results. So that gets us through the second portion of this. Now we're going to get to where we're including Ryan Field's fairing for Santa Sleigh. So in this particular case, we're going to clone and modify the Mach 1 project like we did before, but we're going to use the CAD configuration that includes the fairing. And then we're going to have to modify the surface goal settings to include those for looking at fairing in our CAD geometry. All right, so at this point what we would do would be take this Sleigh at Mach 1, clone this project. This time it would be with fairing, and we would choose the configuration with the nose cone. All right, so I'm not going to clone that one. We'll just switch over to the one that's already solved. And here you can see now we've included Ryan's fairing in our design. And how we changed that, that goal is instead of just using the sleigh, we also have to look at what happens when we include any drag forces on the front of the fairing. We would do the same thing with lift, and then no changes to our drag coefficient. This is the actual equation that I'm using in this, so it's twice the drag force divided by fluid density times velocity squared times the frontal area of the fairing and the sleigh. All right, so let's go ahead and load in these results here. And while those are loading, what we're going to take a look at, just like before, cut plots, pressure, velocity, maybe we want to look at surface plots, any of the other post-processing options from flow simulation are completely valid here. So let's go ahead and take a look at what happens with our results once we've added that fairing. So here we can see, let's see, that's our velocity plot. Let me switch to the pressure plot. That'll make a little bit more sense. All right, so like before, we have a very large buildup of pressure right in front of the fairing. We still have a little bit of recirculation that is right behind the windshield of Santa's sleigh, a little bit of recirculation inside the sleigh, and then still a little bit of air recirculation right behind the sleigh itself. So interesting, by adding in the fairing, I'm not quite sure if we helped the aerodynamic properties of the sleigh or not. Can't really tell just by looking at a pressure cut plot or even the velocity cut plot. So what we would really need to do here would be get into our goal plot and see what happens if we helped or hindered our design by adding in Ryan's fairing. So we'll go ahead and show those results. And then here are the new values for drag force, lift force, and our drag coefficient. So I know those are pretty small to show on the screen, so we'll switch back to PowerPoint. At least I think I'm switching back to PowerPoint. There we go. And we'll take a look here. So our final results, including the fairing, we have a drag force now of 333 newtons, a lift force 210 newtons pushing down, and an even higher drag coefficient. So the drag force went up, our lift force went from helping to actually pushing the sleigh back towards the ground, and we increased our drag coefficient. So in the big scheme of things, what that really tells us is we need to talk with Ryan about his design of a fairing for Santa's sleigh. So here's the good thing. By using flow simulation with Ryan's initial design of the fairing, we've realized that maybe it's not the best design for actually improving the aerodynamic capability of Santa's sleigh, but that's actually a good thing because we didn't have to build one and actually find out that we didn't do ourselves any favors by adding on the fairing. It tells us, well, we should probably go back and modify the CAD design so that we ultimately reduce the drag force and maintain some amount of lift force for Santa's sleigh. And if we do those two things, I'm quite certain we would improve our drag coefficient. So there are just a number of things to cover with getting Santa's sleigh running at Mach 1 using SOLIDWORKS Flow Simulation. And the topics that we discussed today were creating flow projects, setting up boundary conditions, mesh controls, and even goals. And then we went through solving and post-processing the results. We also did cloning configuration or cloning flow projects to different CAD configurations, and modifying boundary conditions and goals to match. And ultimately, we solved for drag forces, lift forces, and coefficient of drag as Santa's sleigh is flying at Mach 1. So, if there are any questions at this time about today's webinar, please feel free to type them into the questions window. And I thank you very much for attending our How to Solve It webinar today. If you're a design engineer and you want to learn more about incorporating SOLIDWORKS Flow Simulation into your work, please go to 3D Vision Technologies website or contact your 3D Vision Technologies account manager today. So thank you very much, and let me take a look at our questions panel and see. Okay. All right, it doesn't look like there are any additional questions. So again, thank you very much for attending today's How to Solve It webinar series, getting Santa's sleigh running at Mach 1 in SOLIDWORKS Flow Simulation. Have a great day and a Merry Christmas, everyone.